Hey, today we're going to talk about absolute extrema and the extreme value theorem. First, we need to remind ourselves briefly about intervals and interval notation. A closed interval, which is written with square brackets, includes the endpoints. For example, the closed interval from A to B, all the points between A and B, including A and including B. An open interval, on the other hand, does not include the endpoints. In interval notation, we use parentheses to designate that, and so the open interval from A to B, all the points between A and B, but not including A and not including B. And this brings us to our main theorem of the day. It's the extreme value theorem. If we have a continuous function f and it's continuous over some closed interval from A to B, then f has to attain an absolute maximum and an absolute minimum at some points in the interval from A to B. And here we have a couple of examples, two functions f that are continuous on a closed interval from A to B. And if we look at the one on the left, it attains an absolute maximum right here at B. That's the largest value that it attains anywhere. And an absolute minimum right here at A, at the endpoint at A. If we look at this function on the right, well, the absolute minimum value is still at A, but the absolute maximum happens somewhere around there at a critical point for the function. It's at a relative maximum of the function, and so that would be at a critical point of the function. And we've just answered the question of where could the absolute maximum be and where could the absolute minimum be? And the answer is each one has to either be at one of the endpoints or at a critical point for the function. And this suggests a technique for finding the absolute extrema of a continuous function on a closed interval. First, evaluate the function at the endpoints of the closed interval. Second, find the critical points of the function that fall within the closed interval that we're looking at, and evaluate the function at those points. And then finally, simply compare. The largest of the values that we just found is the absolute maximum, and the smallest, the absolute minimum. And it's worth noting that it's possible that there could be more than one of each. In other words, the function might have an absolute maximum value of 100, and that could happen at 7 different points within the interval. We'll see an example of something not quite as dramatic as that, but something where there's at least more than one. Okay, I'll do this first example, and then there'll be a couple for you to try. So we're going to find the absolute maximum and absolute minimum values of the function f of x equals x cubed minus 12x plus 10 on the closed interval from 0 to 3. And following the steps that we just outlined, first I will evaluate the function at the two endpoints 0 and 3. F of 0 is very simple to compute, it's 10. F of 3 takes a little bit more careful arithmetic. Do the arithmetic carefully, and you find that f of 3 is equal to 1. What's left is to find the critical points and evaluate the function at those. So let's do that. And the critical points are the places where the function is not differentiable, which never happens because it's a polynomial and it's differentiable everywhere, or the places where the derivative is 0. So to find those places, we take the derivative, and the derivative is 3x squared minus 12. And if we want to know where that's 0, we set that equal to 0 and solve. And when you do that algebra, you find that x is either 2 or negative 2. And here's perhaps the only tricky thing about these kinds of problems. The critical point at x equals negative 2 is not in the interval from 0 to 3. And so it's certainly not going to be the absolute maximum or absolute minimum value of this function on that interval. So we can discard it and not consider it for the rest of the problem. In particular, all we have to do is evaluate the function at the one critical point that is in the interval from 0 to 3. We have to compute f of 2. And you carefully compute f of 2 and find that it's negative 6. Last step. We look at the three values we got, 10, 1, and negative 6. And the largest of these is the absolute maximum, and the smallest is the absolute minimum. And so here's our answer. On the interval 0, 3, this function f has an absolute maximum value of 10, which occurs when x equals 0, and an absolute minimum value of negative 6, which occurs when x equals 2. Okay, you try this one. Find the absolute maximum and minimum values of the function f of x equals x cubed minus 3x squared minus 9x plus 1 on the closed interval from -2 to 5. So pause the video, take a minute or two, see if you can answer this question, and when you're ready, start it back up. I know the algorithm that I described to you had us first evaluating the function at the endpoints, but it doesn't really matter. Here I've gone ahead and found the critical points first. The critical points are where the derivative is 0, and those occur at x equals 3 and x equals -1, and both of those critical points are in the interval from -2 to 5. And part of the beauty of doing it this way is now all that's left to do is to evaluate the function at these 4 points, -2, 5, 3, and -1. And all that's really left to do here is a bunch of arithmetic. So be careful with the arithmetic, be especially careful with the signs of things. And when you do the arithmetic, you get that f of -2 is -11, f of 5 is 6, f of 3 is -26, and f of -1 is 6. And so we get as our final answer that this function has an absolute maximum value of 6, which occurs at 2 places, at x equals 5 and at x equals -1, and an absolute minimum value of -26, which occurs at x equals 3. And this is over the closed interval from -2 to 5. Okay, try one more just for fun. Find the absolute maximum and minimum values of the function f of x equals e to the x squared on the closed interval from -2 to 1. So pause the video, give it a try, start it back up when you're ready. To find the critical points, you have to take the derivative. You need the chain rule for that. You treat the x squared as if it were a variable. That gives you e to the x squared. And then you multiply by the derivative of that function you just treated like a variable, and the derivative of x squared is 2x. So the derivative of this function, 2x e to the x. Critical points occur where this function is equal to 0 because it's differentiable everywhere. And when you multiply two things together and get 0, the only way that can happen is if one or the other of them is 0. And so this breaks down into either 2x is 0 or e to the x is 0. Well, 2x is 0 when x equals 0, and e to the x is never 0. There is no real number x that you can raise e to get 0, so there's no solution to e to the x equals 0, meaning that our only critical point is at x equals 0. To complete the problem, all we have to do is evaluate the function at the 2 endpoints and the 1 critical point, and it's very easy to see that f of -2 is e to the 4th, f of 1 is e to the 1st, or e, and f of 0 is e to the 0, which is 1. If you recall that e is some number between 2 and 3, then it's very easy to see that 1 is the smallest of those numbers, and e to the 4th is the largest of those numbers. And so our answer, this function f, has an absolute maximum value of e to the 4th, which occurs at the endpoint x equals -2, and an absolute minimum value of 1, which occurs at the critical point x equals 0. Again, the closed interval from -2 to 1, very important here. If it was over any other interval, we might get very different answers. Okay, that was the extreme value theorem and a technique for finding absolute extrema of continuous functions on closed intervals. There's a homework on it. Take a stab, have some fun. See you soon.